Okay, so I'm here to talk to you about distributed streams. My name is Amy Boyle, and I am a senior software engineer and team tech lead at New Relic. And my team does stream processing on the large amount of data that my company ingests. So this is one of those talks I wish I could have heard when I was starting out with this subject. While I have a diverse programming background, I have been working with distributed stream processing for the last couple of years. So the audience that I think will get the most out of this talk are people that have been working with large-scale systems but are new to stream processing. But if you already know about stream processing, or if you're not used to working with large-scale systems, there's still information in this talk for you. But first, you can feast your eyes on this safe harbor slide that our legal team has encouraged me to add to this presentation. Okay, so I'm going to be using examples from New Relic's data pipeline. So if you're not familiar with New Relic, we do application and infrastructure monitoring. We monitor the full stack from language agents that are gathering data about function calls and DB calls, to information in the browser, like page views, to metrics from on the health of servers. So with this level of visibility and over 17,000 customers, we have a lot of data. And we do stream processing on basically all of that data at some point. So why am I talking to you about stream processing today, and why has New Relic invested so heavily on it? We live in a world of real-time data. Getting results for your data by processing the data as it comes in can offer better latency, resiliency, and be more efficient. To illustrate this point, here is a grossly oversimplified diagram of what New Relic's backend architecture used to look like. We have our agents here, posting data to our servers, labeled collector, which is doing some processing and saving the data to a database. Then we have a query poller application, which is periodically polling the database for some latest data of interest. A use case for this would be to alert off of the queries. So all of these arrows are synchronous calls. So if something goes wrong or slows down with the processing or in the database, we can have a system-wide catastrophe. Data is lost. That is bad. So instead, we have something that looks more like this. Now, this collector application does little more than just accept the payloads from the agents and immediately dump it into a durable queue. Then we have a separate application, which is reading from that queue, doing some processing and writing it to the database. This puts a layer of asynchrony between our data ingest and our processing, which means we're less likely to lose data if something goes wrong. Additionally, we can have our query processor drink from the same input queue, reading the fresh data just once as it comes in, offering better latency and having more resiliency since it's not tied to the other application. So I've divided this talk into 3 different categories that I think will provide a foundation for someone wanting to build a stream processing system of their own. I can only fit so much into a 40-minute time slot, so this is really just a sampling of the sorts of things you could do for either the fundamentals, the scale, or the operations. So I picked out things that we've found on my team to be particularly useful. So we'll get started with fundamentals. How many people here have used a stream processing system or built one? How many have maintained one in a production environment? Okay, less. Awesome. So stream processing is when you're doing processing on an unbounded or infinite data source. We're also talking about real-time data and unordered data. And you're going to be processing it in a continuous fashion. So this is as opposed to the traditional batch processing where you have your entire data set before you start. So it's a finite data set, usually of some time in the past, and you can just process it all at once and get your answer. Early stream processing systems used what was known as microbatching, which is taking that unbounded data source and dividing it into batches and then periodically running batch jobs. Continuous processing is when we're processing each piece of data immediately as it comes into the system. This will offer us better latency, but when we have processing that's more complicated than simple element-wise transforms, we can find that we can run into issues. Like, how do we know that we've got all our data? How do we deal with late data? Can we trust our results? Early stream processing systems offered low latency but incorrect results, or inaccurate results. Today, we can make the trade-offs ourselves between latency, accuracy, and have eventual correctness. So distributed stream processing, then, is when we have so much data that we can't fit it on one machine or in one queue. We need to distribute our data in order to process it. So for examples for the rest of this talk, I'm going to be using a slice of services that my team is responsible for at New Relic. Do not overwhelm the audience with the entirety of the complexity of New Relic's backend data architecture. I have used examples that actually come from a different point of the pipeline, but I fit them into my example framework. All of the examples that I give are actually things that I've worked on at a high volume of data. So here's our example pipeline. This is going to be a pipeline which has a lot of different data sources contributing to our first queue. And then we're going to be filtering and matching the data according to some registered rules and publishing data that data onto the next topic tagged with what it matched to. Then we're going to aggregate it and publish our results. To provide more context as to the data that the system is processing and what the processing that it is doing is, I'm going to introduce event data. Event data at New Relic is fine-grained nuggets of monitoring data. It represents a single action or event at a single point in time. It's basically a bag of key value pairs that we call attributes, one of which is a timestamp to represent the time that it occurred. The best way to view this data is by using our in-house query language NRQL or NRQL. So we have an example NRQL query here, which is just selecting all of the attributes from some transaction event filtered to an app name. And in the table, you have just the key value pairs, the attributes listed out. More commonly, you're going to be running some sort of aggregation in order to see this data. So here is an example of a time series chart where we're taking the max of the system CPU present for some node status event, also filtered to an app name. As you might imagine, we're heavy users of our own product. So in addition to this being our example processing, there'll also be many of these charts throughout this talk to kind of support some of my points. This data goes to live at rest in our custom-built DB, but my team was birthed out of that team in order to fill the need of processing the bleeding edge data as it comes in. A use case for processing the streaming queries, which would be alerts. So a user will register a NRQL query and then some threshold, and then we'll process the data as it comes in, letting the user know if that threshold gets crossed. That's the simplest case anyways. So here's our example pipeline with our example query. Note that the threshold application bit is actually going to be happening downstream, so we're not going to talk about that here. And also, while this is a single chain of streaming applications, that's not necessarily the case, and in fact, it isn't in reality. There is actually branches off, but we're going to keep it simple. So the first step here is collecting all our data. So we have all the different agents and APIs from New Relic that will all end up putting their event data onto this input queue. I'm going to use the term queue interchangeably with topic because our messaging bus here that we use is Kafka. And we've written this streaming framework ourselves using Java. How many people here use Kafka? How many people are using like a different message bus? A lot of Kafka users. Okay. Okay, so after we've got all our data on our first input topic, we're going to then be reading in that data in our filter match service and matching each event to any registered queries. So we'll be looking at the event type and any filtering attributes. And we're going to, for each event, we're going to find any and all matching queries, and then we're going to tag that event with the ID of the queries it matches. So, and it can match, if it matches more than one query, we'll end up putting out more than one event onto the next topic. This is called a map, or more specifically, a flat map operation. And it's an example of an event-driven process. This is called event-driven because it is the arrival of events into the system that materializes our output messages. The next step will then be to take all of those matching events for a certain query ID and aggregate them according to the registered aggregate function. But how do we do that? How do we know we have all our events in order to aggregate them? Well, we're going to need to window our data in order to be able to produce any results. So this is dividing time into time buckets and periodically publishing results by sorting the events into appropriate time buckets as they come in. So this is an example of time-driven processing, commonly used in aggregation. And this is time-driven processing because our results are materialized by the passage of time instead of the arrival events in the system. So we're periodically just saying, OK, publish this bucket, publish that bucket, the next one. How we get events into the time buckets can be done in one of two ways, either using event time, that is the timestamp on the piece of data that was put on there from when it was gathered, or by using processing time. Processing time is just going to ignore the timestamp and just have a current bucket and be collecting events into this current bucket and periodically publishing the current bucket. This is a very common way that early stream processing frameworks were doing this sort of processing. But this has limited utility because it often leads to incorrect results. Because more often than not, the type of processing you want to do actually is interested in that event time, and you do want the events sorted into the correct buckets as according to the event, the timestamp that was originally placed on the event from the source. So these are not interchangeable. You probably want event time, but it does mean we have to still worry about the late data and the unordered data. So there's a few different ways that I'm going to talk about ways you can window. The first is doing fixed windows. So this is also called tumbling windows. This is when the interval of the window is equal to the window size. Each data point will belong to exactly one window. Sliding windows are when your interval is smaller than your window size. So you have overlapping windows, and each piece of data may belong to more than one window. This is something you can do to get, say, a rolling average. Session windows are when the timestamps on the events themselves are determining the window boundaries. So you'll have some sort of threshold when pieces of data are close enough to each other. They're all in the same window. And you'll probably have gaps between your windows. This use case for this would be something like representing user sessions for users that are logged into your system or just using your website. The examples for the rest of this section are going to be using fixed windows. So we sort events into windows as they arrive into the system. So we may be needing to open up several windows at a time because our data is unordered, and we're just going to have to be able to do that. But the trick is, when do we publish the results? Because we still have this endless stream of data. It's out of order. We don't know when we have it all. So if we do decide to go ahead and publish it, then what do we do with late data? So to tackle the first question of when do we decide to publish, I want to introduce the concept of allowed lateness. We codify this in NERCL using a sense and until clause. So in this example, we have 3 minutes ago until 2 minutes ago. It means we have a bucket size of 1 minute and an allowed lateness of 2 minutes. So we're going to wait for 2 minutes to collect events before saying this is probably good enough. We're going to publish our result. And the simplest way to do this is by using the time basically now on this machine you're processing to determine the edges of the bucket window when the time bucket ends and when it has been 2 minutes since then. But an alternative way to do that is with watermarks. Watermarks are a heuristic based on the event timestamps and based on the flow of the event timestamps into the system to determine when to actually publish the results. Now, this is actually a fairly complicated topic that deserves a talk all unto itself, so I'm not going to get any more into watermarks other than to let you know that they are out there and they can be very useful. So we have our allowed lateness. We'll publish our result, but we still will have late arriving data because we can never have any guarantees. If you're dealing with mobile data, things can show up even hours late, right? So the simplest way to deal with this is to just publish once and then drop any late results. Alternatively, we can publish updates. So after we've published, we keep in memory the aggregate state so that we can add aggregates to it and publish a full update of our result. Another option would be to publish deltas. So this, after we've published our initial result, we sweep away our aggregate memory. But if we get late data, we publish a new result that's just to serve as a difference between the last one and any successive results. Which one you can use is going to depend on your use case, what kind of accuracy you want, and what your downstream consumers are doing with the data, whether or not they can deal with deltas, for example. We can also use a combination of these things. We can have what's known as a late event horizon. So we're after which we drop data, but before which we want to publish updates. So if we had a late event horizon of 10 minutes and an allowed lateness of 2 minutes, we'd wait 2 minutes to gather most of our data, publish a result, then say for the next 8 minutes we're going to publish updates. But after that, we're just going to say forget about it, no late events after 10 minutes. OK, so that's some of the basics of stream processing. So let's talk about how we can scale our system. And of course, we're going to be scaling horizontally since this is a distributed system. We're going to be adding more nodes. So I'm going to zoom into our filter match service here, which we're going to scale that. And we're also going to scale horizontally our input queue into multiple partitions. So I'm going to be representing how to partition or distribute your data onto the different partitions using colored tiles. Being able to scale your streaming system is about knowing how to partition that data in order to spread your load in a way that will work with your logic and downstream consumers. The easiest way to do this is just by randomly sorting out the data. This will give you the most even spread of load you can get, and it works excellent with stateless operations, which don't necessarily really care which piece of data that they're consuming as far as their internal state is concerned. So it'll look like this with any key ending up on any partition. This is something that we use for the filter and match service. So any of the data sources will partition data randomly. They'll place data randomly onto any partition. And because the filter and match service is stateless, it doesn't need to open up any new state for when it's reading data in. It does mean that each instance of this filter match service must know about the entire set of registered queries, however. So as long as we can fit those in our memory, we're cool here. Another way we might need to partition our data is if we're aggregating. So you need all of the data that you're aggregating on to end up in the same place. So all your keys for a certain data will need to be on the same partition. You might have multiple keys per partition. That's fine, of course. And this is what we do between our filter match and aggregate service. So that going into the aggregator, that we have all of the data for a single query so that it can end up in the same bucket to be evaluated into a result. Another reason you might be partitioning data by some sort of key is if you have another resource which is also sharded or partitioned, like a database shard, or if you've written a database and you need to index it, and you want to minimize write locations, for example. This is going to look pretty similar to that last one where we have some sort of attribute of the data that we're going to need to use as a key in order to sort our data onto partitions. It can be very lopsided. You'll find that in some situations you have one attribute of the data that leads to a very large volume of data while others are just a trickle. For example, in our multi-tenant system, we have some accounts that are massive while others that are actually quite small. So in a lot of cases, we're able to actually break up the larger accounts and kind of sub-partition those and spread them across many partitions so that we don't have some partitions that are very overwhelmed. It can make it hard to scale if you're just trying to move around monster accounts or attributes or whatever it is. So it'll be context specific on the way you're able to break this up. So I'd like to discuss one aspect of this sort of messaging queue connected microservice architecture that's been impactful to our high throughput streaming systems. So for this, I'm going to tell you a bit of a story. So this pipeline here used to have another service in the middle of it. We had this service which was basically taking batches of events, turning them into single events, and then doing a pre-filter stage on them before forwarding them on to actually get matched to their queries. So this was also an event-driven process, relatively simple. We were doing some thread profiling on this system, and we kind of knew this, but when we saw the data that the very large majority of our CPU was being spent on serializing and deserializing data, we're like, maybe this doesn't really need to be in its own service. So we squished the logic from the pre-filtering stage into the filter and match service, and we're able to drop an entire queue. This was the right this is the right trade-off for us. It's a small code complexity cost for a large performance gain. And I want to point out also that at this point, we're kind of at an optimized state. We can't squish this any further because we have many different data sources that need to collect data onto that first queue. And in this queue, we need to repartition our data according to the match that happened at this stage in order to be able to aggregate it. So this is a fully optimized chain here. And this chart is a demonstration of this is a normalized measure, but it's showing the number of CPUs we were using for both services before and after, and we basically got to eliminate one of our largest services and an entire topic. Moral of the story is serialization is expensive, and think about your microservices architecture and make sure it's not venturing into the nanoservices space, at least when you're talking about high throughput systems. This wasn't such a big deal when we built the system when it was really small, because the numbers were just small in general and it didn't didn't matter that much. But as we were growing, when we were having to scale things out more and more, being able to eliminate one of our large steps was actually kind of a big deal. Another kind of tip that's related to this is if you can have some sort of separately deserializable piece of data, either a data key or some header data, that you can use to determine whether or not the payload is of interest, this can also save you lots of CPU time. For example, if we have account ID as our key, we can look at the account ID and look to see, do we have any queries registered for this account at all? If the answer is no, we say, drop this payload. We don't need to process it here. So the last thing I want to talk about in this section is the use of back pressure. Don't have unbounded queues in your application. They will fill up and blow out if you receive traffic spikes. This is actually the default for a lot of Java libraries, by the way, which we found out the hard way. Do have bounded queues between your I/O bound and your processing and your CPU bound processing threads. This is going to allow you to separate your I/O bound and CPU bound processes in order to more smoothly optimize your resources. It's also going to allow us to fan out our processing. So this is where we put that expensive serialization and deserialization, leaving our consumer and producer threads free to do I/O and not cause any conflicts or backup there. The queues outside of your system that you're using here should be durable and replayable if you care about having correct results. This is because if this application were to go down, to crash, we might lose any in-progress data. We need to be able to back up on the input topic and reread and reprocess that data so that it gets published. Okay. So at New Relic, we do the DevOps. That means that in addition to building this system, we're also responsible for testing it, deploying it, and we carry the pager. So let's talk about the inevitability of things going wrong. For us, we tend to try to follow the same code paths for restart and deploy as we do for a failure recovery scenario. So for us, deploys are more like a graceful failure with auto recovery and some code changes snuck in. This ensures that those failure recovery code paths, or at least some of them, are getting a regular exercise in production, so that if we have unrelated changes, or what we think are unrelated changes, we kind of see some of that stuff pop up earlier. So because we're expecting things to go wrong, we're of course provisioning headroom. Now this isn't new. Even if you don't have a streaming or distributed system, you should always be tolerant to host, rack, or even data center failure, depending on what your scale is. But how we make sure that we have that headroom provisioned might look a little bit different depending on our architecture. So for example, if we have 4 instances of our streaming service here, and we were to, and they have 40% headroom, this should be plenty, right? If we were to lose one, though, we don't have some like F5 load balancer to evenly redistribute the data to the other remaining instances. We're going to have some unlucky instance that's going to get an entire data partition's worth. So we need to make sure that we've provisioned extra instances in a way that's going to allow the correct number of instances to accept whole partitions of data more. So I also want to talk a bit about how we move those partitions around when instances come up or go down. The easiest way to do this, logically, is with random assignment. So if we lose an instance, everyone else forgets about their assignment, they get reassigned, and they continue reading from there. This is great for stateless services, which aren't necessarily caring about what it is that the data that they're processing. They can just accept it and process it and move on. For services that we have that are maybe opening up data structures, depending on what data that is that they're reading, probably some sort of keyed data, this can cause issues, particularly when we're talking about we're doing a rolling deploy. So we can't have downtime, so we're doing a rolling deploy, which means we're going to have a lot of these rebalances per deploy. The bigger the service we have, the more the rebalances probably. So we might want to use something like a sticky partition assignment. So this will, when we lose an instance, it'll try not to move things around too much. If we lose an instance, it'll try to move that instance to another instance which maybe doesn't have as many partitions, or if they're all the same, just another one. It's going to still try, we still want to try to keep the number of partitions per instance balanced, but we're going to try to reduce the thrash that we have. But in this situation, our instances still do need to deal with having their partitions reassigned at any point in their life. The last example that I'll give for this is with fixed assignment. So in this case, we don't want our instances to deal with having partitions move around on them. So once they get a partition, they're going to hold on to it for life and not accept anymore. So if we were to lose an instance, nothing's going to happen with this partition. It's going to go unconsumed until another one comes along to pick it up. So in practice, if we're using this strategy, we're actually going to have another instance here ready and waiting to pick up the partition in case any are dropped. So I want to do a little bit of recap because I've mentioned stuff that works with stateless and stuff that works with stateful services as well. So stateless services are most commonly event-driven. They work well with a random partition assignment that is putting any data on any queue because our systems can deal with that since they don't have state. And also with random rebalances. They don't mind if the partition they're reading from gets switched out on them at any point. Stateful services you'll have them with aggregation. They are often, but not always, time-driven. You're probably partitioning by some attribute of the data. And this is a situation where you're likely to want sticky or fixed rebalances when you're reassigning partitions when instances come and go. Now, this has not been a comprehensive discussion of rebalances or partition assignment or any of that. These are just some of the most common things that we've come up with. Your mileage may vary, and there may be different sort of situations where you'll want to do some custom stuff. Another thing that's been important for us when it comes to deploying and failure recovery is snapshotting when we have aggregation. So we have that configurable allowed lateness in our NERCL clause, and that can be up to several minutes of allowed lateness. In a high throughput real-time system, that is a lot of time. So that is a lot of data. We can't really afford to actually back up several minutes and not have some sort of and not have our results also be late. So we've introduced snapshotting here. For us, we're actually using another queue, another Kafka topic for that. You can do this with any sort of database, but we've chosen to use another queue because it's going to give us implicit hierarchy with the partition management and also to reduce dependencies. So I'm going to go into a bit more detail on that. So we have our input topic here with 3 partitions. And we're also going to have our snapshot topic also have exactly 3 partitions. We want to make sure these numbers match. If we increase the input topic, we're actually going to make sure we increase the snapshot topic number of partitions first. But I'm going to make the output topic go away right now, just so we clear some room on the diagram. We're going to have a 1-to-1 match with our input topic partition and our snapshot topic partition. So we're going to be snapshotting to the matching partition. We're aggregating our state in our aggregator, and we're going to periodically just publish a snapshot of that state, tagged with the key will be the query ID and also the bucket, so like the start time of the bucket. We're also going to publish tombstones. So when we publish a result, we're putting a tombstone also on that snapshots topic to let us know that the snapshots we had previously put there are now no longer valid. So when we start up, we're going to get our assignment for our input topic. And then we're going to go grab the same partition from the snapshot topic. We're going to read in that entire partition, deduplicating based on the keys. So we end up with our deduplicated set of snapshots. And we're dropping those snapshots for which we encounter a tombstone. Also saved with the snapshot is the starting point on the input topic. So that represents the place at which that snapshot was taken, so that we're able to then start at the appropriate place without and have correctness in either the regular restart or the failure scenario. Then we're able to start processing as regular, publishing snapshots again, circle of life complete. So because we're DevOpsing, that means we're in charge of making sure our system is observable and that we have the adequate monitoring in place in order to do so. Keeping track of what's happening in a distributed system is a little more complicated than monitoring response times and CPU usage. We need to be able to collect data that we can aggregate and facet that's going to tell us about the state of the cluster in general. Some questions we might want to ask ourselves are, how do we know our data is being consumed? How do we know we're not double consuming data? We have a bunch of different ways that we monitor our distributed streaming systems. We use aggregated metrics, we use events, we use traces, we use logs, we use error information. I'm just going to give a couple, and it's usually very dependent on what part of the system we're looking at. But I'm going to give a couple examples of things that we use that we tend to use across all our streaming applications. One of them is this partition ownership event. So this is tracking which instances are consuming which partitions of data. So this will tell us if we're double consuming or not consuming at all. So in this example, we actually have an example of things going wrong, where we have some partitions being consumed by multiple instances. This is bad. This is something we get alerted off of. So in the middle of where this noise is, we have a deploy happening, and then the fix is deployed, and everything's at exactly one where it should be. We also are tracking our throughput metrics. This is something we're used to have like in a dashboard like this. So in this example, we have the batches consumed by our first application, the filter matcher, some processing step, messages produced, consumed by the aggregator, tracking late events, and then also the results, number of results produced. This is something that's all we can also help use for capacity planning as well, to see historical trends if we look at a larger time scale. At a glance, we can see if something goes wrong here, that it looks like the dip appears between consuming the batches and pre-filtering. That's a bad sign. We should probably look into that. Or if everything kind of looks like this, we might be able to conclude that our problem is actually upstream. Another key indicator we have is data lag. So data lag is the time between which we're consuming data and the bleeding edge of which it's being produced, generated. So if we have the timestamp on the messages of the time that they're produced onto the topic, this is the difference between the latest consumed message by the filter matcher and the latest produced message by our data sources. So we monitor this as well with, here was another custom event. We're tracking the offset lag in this example. We're actually more commonly probably going to be looking at the second lag, at least when it comes to alerting. This is more closely, this is a normalized measure, and it's also more closely related to our SLIs, or SLOs, sorry. And so in this example, we have data lag. This is something we would have gotten alerted for. Did something to make it go away, and we have a fast recovery. So monitoring should not be an afterthought. We need to build observability into our system as we're building the system. This is similar in principle to testing. It's easier to write tests when you have testable code. Think about having monitorable code. This is something that's also, you're not necessarily going to get right from the start either. This will be a process that evolves. Like just last week, we were adding another piece of monitoring for a blind spot that we had. So to recap a bit, some of our must-have dashboards for each of our streaming services would be data lag, data ownership, system throughput, and anything related to our SLIs. This is also, we're also going to have alerts set up for all of these things, at least all of these things. I feel like it should go without saying, but your alerts should be actionable. I think I heard like at a couple different talks that were mentioning about how things went really wrong. Like one of the key factors was people like just snoozing their alerts because they were noisy. So don't do that. OK. Yes. Also important is to make sure that we're adequately testing things. So this doesn't mean writing unit integration tests. There are too many properties or bugs in a distributed system that are emergent. You will not find them in unit or integration tests. You need to be running your code through a test, sometimes known as, or a staging environment, that has realistic data. Preferably, this should be a portion or all of your production data. And it should be running all of the time. Your code should be baking here. Also, it needs to have all of the same monitoring and alerting as your production, so that you have the same visibility, that you're used to debugging it in the same ways. You don't go, oh, that's just the test environment. And that you're alerted to it so that you don't accidentally push stuff to production. OK, so just going to wrap up with a couple final thoughts. So we considered using a stream processing framework when we were building this system. We'd done prototypes and a number of different things, a streaming framework like Flink or Kafka streams. But none at the time offered us the right operability or functionality profile. These frameworks have evolved a lot in the last couple of years, and this is something that we're keeping an eye on and may end up refactoring parts of our system. If using a stream processing framework can abstract away some of the complicated logic, operability, and scalability issues for you, some of which I've discussed in this presentation. Who here is using a stream processing framework in a production environment? Cool. OK. So if you take nothing else away from this presentation, these are the things you can remember. Use a windowing strategy for dealing with unordered and late data. Partition your data effectively so that you can spread load and that will work with your application logic. Serialization is expensive, so think about your microservice architecture. Failure is going to happen. Be prepared for it to make sure you practice it regularly. And keep track of your data flow and your bottlenecks. Think about back pressure. So thank you for listening to my talk. I will be taking questions either up here or in the hall. Find me for the rest of this conference. I'll be around, and I'd love to talk about any of this stuff that I discussed today.